recording now. So just before we get into the lecture material, I'd just like to go over something about the homework you had on Mastering Physics. So there's a Mastering Physics homework in the announcement, and it looked like some of you were having trouble accessing that. I think the problem we had is sorted now, so I don't know if anyone's been able to see that yet, but it should be there available on the Mastering Physics website. I'll put out another announcement after this lecture, but you'll have 2 weeks from now, so now will be the starting date of the time you've got to do that homework. So again, if there's any issues, just let me know. Right, so let's just go over a little bit about what we looked at last week. So last week we started looking at inductance, or more specifically inductors, the circuit element of inductors. So one of the key aspects of inductors is that the voltage that you have over an inductor. So if we have an inductor in a circuit like this, so this is the circuit symbol for an inductor, and we said the voltage that you get over an inductor is equal to the inductance, so how basically a measure of how good this inductor is, how much inductance it has, multiplied by the rate of change of current. So in order to have a voltage over an inductor, we need the current to be changing. So if there's no change in current, we don't get any voltage over an inductor. So then we looked at what happens when the current is increasing. So if or in this case, when we've got a constant current, like we said, if here the current is constant, then we don't have any voltage over our inductor. But then when we've got an increasing current, so the rate of change of current is greater than 0, then we get a voltage over our inductor that opposes that. And then gradually this current will increase, but its rate of increase will slow down and will eventually reach a steady state of current. And in that case, this EMF over the inductor will decrease to 0. And I introduced a water analogy for an inductor. So it's often good to think about how these circuit elements are analogous to elements in a water circuit. So we've looked at this before for resistors, and we said that in a water circuit, the voltage we apply is equivalent to the pressure. So if we've got an inductor in some circuit connected to a battery, then the water analogy to that is having some kind of water pump that can pump water and apply pressure, and then the inductor was analogous to a water wheel. So if we've got a water wheel that can be pumped by or moved by our pump, so it's got some paddles on it, So if this pump can apply some pressure and start pumping water in this direction, then a good analogy for an inductor is a water wheel that's got some inertia to it. So when we start trying to pump water around this circuit, this water wheel will have some inertia. So initially it won't start moving, but then over time it will gradually pick up speed, and once it reaches a steady state, then there's no pressure difference over this water wheel. Once it's got up to the speed it's going to go, then the pressure here will be the same as the pressure here. And equivalently for an inductor in an electrical circuit, once it reaches a steady state, then the voltage we measure over it will equal 0. And then when we switch the pressure off in our water circuit, so if we stop pumping the water, because this water wheel has got inertia, it will keep spinning for some time and keep trying to push the water around the circuit. So in that case, we'll have higher pressure on this side compared to this side. So the pressure difference will flip over then, and the same happens in an electrical circuit. So if we switch off the voltage in an electrical circuit, then this inductor will keep trying to push the current around the circuit in the same direction it was going. Then we looked at what happens in a real circuit that's got a resistor in it. So an ideal inductor has no resistance associated with it. Okay, I've got a question here. So I've got a question. So does it act like a battery or power supply when the current is changing? In some respects, yeah. So it stores energy in the magnetic field. So we looked at how as we apply current to an inductor, we get a magnetic field built up in the inductor, and that's where the energy is stored. So it does store energy in a similar way to a capacitor, how a capacitor stores energy. So a capacitor stores energy in the electric field that you get between two plates. So in theory, you could use an inductor like a battery, but it's very inefficient. So you need quite a lot of weight in there to be able to store a reasonable amount of energy. Whereas capacitors, they are actually quite feasible for storing energy, and you can make them light enough to store a reasonable amount of energy in them, and they're actually used quite a lot in various applications. So their energy storage density isn't as good as lithium-ion batteries, so they can't store anywhere near as much energy per unit weight as a battery. But what they can do is store and discharge electrical energy very quickly. So a lithium-ion battery can only give out and be charged back up at a relatively low rate. So there's applications in electric vehicles. So all electric vehicles, as far as I know, have a very large capacitor in there that can store energy from the regenerative braking. So when you're going along in an electrical car and you slow down, then you start charging up. You're recovering some of that energy as you brake. So it's turning the electric motors in the electric car, and there's actually a lot of power in that, and it's too much power to deliver all in one go to a lithium-ion battery. So these very large capacitors called supercapacitors used in electric cars to store that big burst of energy, and then they can give it out again either to the motor or to the battery and charge it up. But inductors, because of the weight that they need, like to have a good inductor, you need an iron core to be able to store the energy, and they're just nowhere near as efficient as capacitors are at storing electrical energy. So if we've got our real circuit here that's got a resistor in it, so we can either put a resistance in, or this resistance would just be the inherent resistance of the inductor. And we looked at what happens when you flip a switch in this circuit. So you've got a battery here, and then we're going to flip a switch, and then look what happens to the current. And what we see is this curve that's it's a flipped upside down exponential decay. So exponential decay looks like this. This is time, this is intensity, and then after one time period, so it's usually referred to as tau, then the initial intensity drops by a factor of E, so that's going to be 1 over E of this initial value, and then after another time constant, tau, then it's dropped by a factor of 1 over E squared of the initial value, and so on as you go for more and more time constants. The current growth is just this flipped upside down. So instead of starting at an initial value, you start at 0, and then it tends, instead of tending towards 0, it tends to some maximum value. So after some time period, tau, then the intensity has increased by 1 over E of the final value, and so on as you go on for more time constants. So we went through the derivation of this. So we looked at, if you've got this circuit, you can apply Kirchhoff's loop rule, which you've looked at before in the first semester. So we can apply this rule and look at the voltages, and then what we want to get is the current I, because we want to know what happens to I as some function of t. So that's all in this equation that we've got, but we just need to rearrange it. So we went through how we do the arithmetic of rearranging that equation, and then what we do some integrals, and then taking some exponents, and then eventually we can get our equation in a form like this. So we've got then our current. You want to know what's happened to that current over time. So it's some function of time here, and then this number here, this part of the equation here, this epsilon over R. So that's the final current that we get. That's what this tends to as time tends to infinity. And then this part, this R over L, is related to the time constant. So we just need to flip this round a bit. So the form of an exponential decay is e to the minus t over tau. So here in this equation, it's got a bit messy now, but here it's t times r over L. And so we want to know what that r over L is as a time constant. So instead of being that times t, we want it divided by t. So we just flip that upside down. So the time constant then is L over R. It's the inductance divided by the resistance of the circuit. So the bigger this value is, so the bigger the value of L we have and the smaller the value of R we have, then the longer this time constant is, and the longer it will take for the current to tend towards a final value. So similarly, we can look what happens when we have reached a steady current, and then if we open this, then if we close the switch, and once we've reached our steady current, and see what happens when we dissipate that energy that's been built up in the circuit. So initially we've kind of built up the current in the inductor by attaching to a battery. Then if we imagine we disconnect from the battery and then we close this switch so that we can then dissipate the current, then that energy that was stored in the magnetic field of the inductor is then going to be dissipated in this resistor. And then again, we want to know what happens to the current over time. So it's just the negative of what happened with the current increase. So when we build up the current by connecting to a battery, we have this exponential rise to a maximum value. Then when we disconnect from the battery and then discharge to a resistor, then we have an exponential decay. So this is just a simpler function to what we had before. So the equation for the exponential decay, the current decay, is just this equation, but without this 1 minus in it. So that gives us a function like this, an exponential decay that tends towards 0. And then with that 1 minus is what we have, the exponential current growth when we've attached to a battery. But in both cases, the time constant is L over R. So we'll have, if L and R stay the same, then the time constant we have tau. So in the exponential decay, it will be the time taken for the current to decrease from some initial value by a factor of E. And then when we are having the current growth where it's connected to a battery, then we're starting from 0, and then the time constant tau is the time taken for the current to increase from 0 to a value that's 1 over E of the initial value. Okay, let's have a go at a question then. So a resistor and an ideal inductor are connected in series to an ideal battery, having some constant terminal voltage V0. So at the moment contact is made with the battery, the voltage across the resistor is what? Is it V0, V0 over E, V0 over 2, or 0? So if you go to the Poll Everywhere site, polyv.com/markh. So we'll activate that poll. You'll see there's an E, so we know that it's not an option E, because we've only got A to D here. So based on what we talked about, the behavior of inductors, see if you can answer that question. Okay, you've got 4 responses so far. Six responses. Okay, give that another minute or so, see if we get any more responses. Okay, so what we got so far, we've got 2 people have gone for A, the voltage is V0. 2 have gone for B, the voltage is V0 over E. 1 has gone for C, the voltage is V0 over 2. And 1 for D, the voltage is 0. So what we're looking for here is D, 0. So remember, the current has to rise from 0. Remember what the time response of an inductor looked like. If that was the current, and this is time, it has to start from 0 and tend towards some final value. So at the very instant of time where we checked at t equals 0, then that current is 0. So we've got 0 current flowing through our circuit. And so our battery here, inductor here. So at t equals 0, there is no current in this circuit at the instance if we got some switch that we flip. There's no current through this circuit, and for a resistor to have any voltage over it, we need current. If the current is 0, then the voltage that we measure over this resistor, so equals IR. So if the current is 0, then voltage is 0 over that resistor. Okay. So we'll go another question then. So a resistor and an ideal conductor are connected in series to an ideal battery having a constant terminal voltage V0. So at the moment contact is made with the battery, the voltage across the inductor is what? V0, V0 over E, V0 over 2, or 0. Okay, so if you go to the Pull Everywhere site, I've activated that question. Okay, you've got 5 responses so far. 6. Okay, let's give that another minute or so. Okay, so far I've had 3 people go for A, so voltage is V0 across the inductor, and 4 people go for D, it's 0. Okay, so what we're looking for is, the answer is V0. Option A, answer is V0. So I guess this is a little bit trickier to explain, but again we can start by remembering the time response of an. So what happens over time to our current? So it starts at 0, increases rapidly to start with, and then that increase gradually slows until there's no increase at all, and we reach some steady current, I0. So that's t equals 0. We start at 0 current. So as we progress over time, we reach a steady current. There's no change in current. So if you remember, the voltage over an inductor was L di dt. So after a relatively long time, then when we've reached our steady current I0, then di dt is 0. So we've got no voltage over the inductor, but at time equals 0, we've got the maximum rate of change. So right here, if you drew a tangent on there, we'd have the maximum di dt that we're going to have. So to see what the actual voltage is, you can look at the equation and work it out. But I think a better way to conceptualize this is again to come back to our water analogy. So we got some pump that's applying some pressure, which is analogous to the voltage. Then we got some water wheel that's being spun round by that pressure. So this is our pump, so sending some water this way, and then it's our time equals 0 is like when we connect up this water circuit and start pumping water, and then this pump will apply some pressure. So if we had some pressure meter here, which is analogous to the voltage, then if we had some pressure meter, it's going to get messy here, some pressure meter over the inductor, then the answer here is A. So this is just, so that's just part B. It's answer A, it's V0. So if we measure the pressure here, okay, let's imagine we've got some pressure meter here, then at time equals 0, when we initially start pumping this, then this water wheel isn't moving. So nothing can move across it. So it's effectively got an infinite resistance because none of these paddles are moving. The current is 0 at the instant that we start pumping. So all the pressure that we apply with this pump will build up on this side, and here it will remain the same pressure as this side. So whatever pressure we apply with this pump, we're going to have that same pressure at that instant that we start pumping. And then the same is true for the analogous water circuit. So the analogous electrical circuit. So we've got our electrical circuit, inductor in. Then at the instant when we connect up this circuit, then we've got no current flowing here. So all of the bias that we apply, sorry, no current flowing here, all of the bias that we apply from the battery here will be on this side of the inductor. So the voltage we measure here will be the same as the voltage over the battery. So we've got no current flowing at that instant of time, t equals 0. Okay, let's have a go at another question then. So an inductance L and a resistance R are connected to a source EMF as shown. When switch S1 is closed, a current begins to flow. The final value of the current is A, directly proportional to RL, B, directly proportional to R over L, C, directly proportional to L over R, D, directly proportional to 1 over RL, or E, independent of L. So again, go to the Poll Everywhere site. Okay, you've activated that question. So have a go at that. Okay, you've got 2 responses so far. So again, this is quite a tricky one, and it's really testing your understanding of what inductors do. Even if you're not sure, just pick an answer. Okay, you've got 4 responses so far. 5. Okay, you've got 7 responses now. Okay, let's give that another minute or so. Okay, so what we've got so far is had one person go for B, so directly proportional to R over L. Two people gone for C, directly proportional to L over R. And four people have gone for E. It's independent of L. So what we're looking for is E. It's independent of L. So a final value of the current. So what this tends to is over a long time, that final value of the current is independent of L. Right, so again, come back to our time response of an inductor. Right, so over time, our current looks like this, starts at 0, increase, the rate of increase slows, and it tends to some final value. And then the question was, what is that final value related to? So if you remember, then the voltage over an inductor is L di dt. Right, so at the final value, so over a long time, di dt is 0. So this part will tend to 0, and so the voltage tends to 0. And then when we've got no change in current, the inductor isn't doing anything, right? An ideal inductor, if there's no change in current, if we've got a steady current that's been steady for a long enough time compared to its time constant, it doesn't exist, right? That may as well just be a wire, right? Because we've got this di dt component for the voltage over an inductor. It's got no voltage over it, so its inductance doesn't count for anything. It doesn't matter how big this inductance is, and multiply it by 0, so voltage across it is 0, and as far as the circuit is concerned, it doesn't exist. So the final value only depends on the EMF and the voltage. So that final current then be the EMF over resistance. It's independent of L. Okay, let's take 10 minutes break there. I'll see you back here in 10 minutes. Okay, let's make a start then. So let's have a go at one more question and then we'll move on to something else. Okay, so final question on the time response of inductors. So here we've got an inductance L and a resistance R that are connected to a source EMF as shown. Initially, switch S1 is closed. Switch S2 is open and current flows through L and R, the inductor and resistor. When switch 1 is opened and switch 2 is simultaneously closed, the rate at which this current decreases is A, it remains constant, B, increases with time, C, decreases with time, D, any of A, B, or C is possible, or E, misleading question, the current does not decrease. Okay, so think about that one. I'll activate the poll everywhere site. So this question is just asking what happens to the rate at which the current decreases over time. So we've built up a steady current, then we open this switch and close this switch. And it's saying what happens to this current I that's flowing in the circuit over time, the rate of that current decrease. So you know it's going to decrease as it discharges through the resistance. So saying what's happening to that rate over time. Okay, got 3 responses so far. Okay, give that another minute or so and go over this. Okay, got 5 responses now. Okay, so I had 5 people go for C, and that's it. So it's great what we're looking for. There's C, it decreases with time. So if you remember what happens when we're discharging current, it decreases exponentially. So over time, it starts at some initial value, decreases, and then tends towards 0. So at time 0, we start off with an initially very fast decay, and then over time, because the form of an exponential decay, that rate at which the current is decreasing slows and eventually tends to 0. Okay, good. Right, let's move on then. So we've looked at the time response of inductors. So let's have a look at a really important type of circuit. So a really important circuit in analog electronics is the LC circuit. So a capacitor connected to an inductor. These are really useful circuits, and it's how they behave over time that is what makes them really useful. And this stems from the ability of inductors and capacitors to both store energy, but the way in which they store energy when they're connected together, they work in a very special way. So imagine we've got a capacitor here just connected up to an inductor, and there's nothing else in the circuit. Obviously, we've got a switch here. So what we're going to imagine we initially start off with the capacitor charged. So maybe we could connect this some other way to a battery and charge it up. But we're going to start off with this not connected together, and then we'll look what happens when we flip this switch. So we start off with some particular potential difference over the capacitor because it's charged with some charge, and then the amount of charge that we get on that capacitor depends on the capacitance and the voltage. Right, so I've looked at this in the last semester, the relationship between voltage, charge, and capacitance. So the better a capacitor we have, so the more capacitance it has, the more charge it can store for a given voltage. So if this is a really good capacitor and we charge it up with a particular voltage, then that will have a lot of charge stored on it. So we start off with 0 current, the capacitor is charged and there's no current flowing in the circuit, and all the energy is stored in this electric field in the capacitor. So down here we've got a little bar chart showing the energy. So we've got here this brown bar, that's the total energy in the circuit. And then here we've got UB, so that's the magnetic energy stored in the inductor. And then we've got UE, that's the energy stored in the electric field of the capacitor. So when we start off, all the energy is stored in the electric field of the capacitor. And if we imagine there's no resistance in this circuit, then we're not going to dissipate any energy. So the total energy remains constant. It's just going to move back and forth between the energy stored in the capacitor and the energy stored in the inductor. So when we flip this switch, so we're now going to flip this switch so that now we connect the capacitor up to the inductor, and then that charge that was stored in the capacitor is then going to discharge through the inductor. So as the capacitor discharges, the current increases, but the rate of change of current decreases. So at that instant, we've got the biggest rate of increase in current, but then that will tend towards 0. And then once all that charge has has discharged and the capacitor potential becomes 0, then the induced EMF is also 0. And so we're going to end up with no change in current, even though the current has reached a maximum value, so that then the voltage over the inductor is 0. And it's going to level off at some maximum value, call that IM. And so once we've leveled off at that maximum value, all the charge has been dissipated from the capacitor. So the energy in the electric field in the capacitor is 0. And now the magnetic field in the inductor is at a maximum. We've got to our maximum current value. So all of the energy is now stored in the magnetic field of the inductor. Then, as we carry on in time, so although the capacitor was completely discharged in the previous step, because of the way an inductor works, so once the charge stops coming from the capacitor, the inductor is going to want to keep pushing the current in the same direction. So the inductor will keep pushing charge in this direction, and that will then start building up charge on the opposite plate of the capacitor. So that inductor then is going to start dissipating its energy. So that will start at some maximum value, but eventually the current and the magnetic field will reach 0, and the capacitor will be completely charged. So, but it'll just have the opposite polarity. So again, in this situation now, the energy in the magnetic field is now 0. All the current has gone from the inductor, and then the capacitor is now completely charged. So if no charge was lost in the circuit, then all of that charge is now on the opposite plate of the capacitor. And again, the total energy of the circuit remains constant throughout this process. And then now the reverse is going to happen. So the charge that was built up on this plate is going to flow back through the inductor. We're going to build up a magnetic field in the inductor. And then once that capacitor is completely discharged, then the current will reach its maximum value again. And in this case, all the energy is stored in the magnetic field of the inductor. So we now go back to having all the energy stored in the inductor and nothing stored in the capacitor. But then as we progress in time further, then this magnetic field, because we've reached this steady current, the inductor is going to keep pushing current in this direction, and then we're going to start building charge up on this plate of the capacitor. And that takes us back to step 1. So you can see we've got this oscillatory motion in this inductor. So as long as there's no losses, then the circuit will oscillate at a particular frequency. So it will send current back and forth, and there'll be some particular frequency that depends on the capacitance and the inductance of this circuit. And I think now would be a really good time just to introduce some of my current research that is related to this phenomenon. So one of the things I'm looking at is building or developing materials that could be useful for quantum computers or quantum communication. And one of the things I've looked at is using a very special type of these LC circuits. So we'll just step back a bit and go over the kind of introduction to this research. So what I look at is something that could be useful for quantum computing, but going back to classical computers, so the computers that we use now, then the data is represented by ones and zeros in the circuit, and this could be represented by a voltage or no voltage usually, or light or no light, for example, in an optical fiber or in a CD recorder, or a magnetic field up or down in a hard disk. And the number crunching, so the processing of these numbers, is done with logic gates. So for example, this is an AND gate, and it follows a certain logic pattern for the output and the input. So we only get an output when we've got a 1 and a 1 on the two inputs. And there's different types of logic gates, but if you connect them up the right way, then you can, for example, build a simple adder here. So this just adds two small numbers. And then if you just scale this up further and further, then you can build the type of microchips that are in your computer or mobile phone. So there's just very big versions of this adder, essentially. But there are some problems for classical computers that are really difficult. So there's certain problems that require every solution to be tried. So, for example, finding the prime factors of a large number, or searching an unsorted database, or finding the quickest route through a network, or protein folding problems. These are all very difficult problems for classical computers to solve, because you need to try every possible solution. There isn't an analytical solution where you just follow through. And if there's enough solutions to be tried, then this can be very difficult for classical computers. So, for example, take this number. It's a really big number, but there's two prime numbers that multiply together to give this number. And so we can try and get a computer to solve that. And say we've got the most powerful computer in the world to find the two prime numbers that multiply together to give this number. Then the time it would take currently for that computer to solve this problem is greater than the age of the universe. So there's some problems that are just really difficult for classical computers. So with quantum computers, data is represented by systems in what we call quantum superpositions. So this data is stored in qubits, and there's lots of different phenomena, physical phenomena, that can be in a superposition. So, for example, an electron has a property called spin. So it can either be spinning around one way, we call it spin up, or spinning the other way, we call that spin down. And it can also be both at once. Similarly, we can have electrons in the energy levels of an atom, so it can be one state or another. It can also be in both states at the same time. There's also the polarization of photon, so you can have a photon polarized vertically or horizontally, and it can also be polarized both ways at the same time. So in this way, if we represent our data with a qubit that's in a superposition of states, then a qubit can represent a 1 and a 0 at the same time. And then we can connect qubits up together, and then we can gate them, so we can switch them on and off. And if you build up a complicated enough network of qubits that are gated, gate them in the right way, then you can program a quantum computer to solve any particular problem that you would like it to do. And then because these qubits can be a 1 and a 0 at the same time, in a sense they can try every solution in one go. So this means that we can solve certain problems almost instantly with a quantum computer. So one of the leading candidates for quantum computers use superconductors. So the qubits are in superconducting circuits, and the reason why we can use superconductors as qubits is because when we get a superconductor, so we usually need to cool it down to very, very low temperatures, but once a conductor becomes a superconductor, all the electrons in there take on the same state. So it behaves like a single quantum system, where it's in one state or another. Whereas if we've got a conductor that isn't superconducting, all the electrons in that conductor are doing their own thing. It's not like a single quantum system, which is in one state or another. So this here is showing what's known as the insides of a dilution refrigerator that's used in a superconducting quantum computer experiment. As you can see, we've got a whole load of connections in there, and this complicated refrigeration system is needed to get down to the very low temperatures that are needed by superconductors. So you need to get down typically to within a few millikelvin, so maybe about 10 millikelvin, so about 10,000ths of a degree above absolute zero. And then this is what a superconducting quantum computer actually looks like. So it's patterned on a microchip that's got some superconductors on there, and this goes inside here somewhere to get it very cold, and then it's connected up. And currently these are the most sophisticated quantum computers around, these superconducting quantum computers. And currently I think the record is about 70 qubits. So it's about 70 qubit devices on a single chip, which is really low compared to the classical computers, which have billions, maybe 100 billion or so transistors on them. Currently, you can only get 70 qubits on a quantum computer. So at the moment, these can't do very much. They still suffer a lot of problems with decoherence, where these delicate quantum states are lost. But it's very promising, and I think recently what's known as quantum supremacy was demonstrated for one of these superconducting quantum computers, where there was some certain type of problem that this quantum computer could do better than the most powerful classical computer. But this is still very much in development. And it's not only superconductors that are being looked at for this. So there's lots of other platforms, and one of the main ones is quantum dots. And one of the groups that has made a lot of progress, so this is UNSW in Australia, that's the University of New South Wales, and quantum dots occur when you confine electrons in a small space. So if you manage to confine electrons in a very small space, it behaves a bit like an atom. So those electrons that are confined will be in one state or another state, so they'll behave like a quantum system. So you can build devices that do that. So this is showing a microscope image of a quantum device, and these metal patterns here, so these are gates, and there's voltages applied to those gates that confine electrons in particular spaces here, so we can confine them at two particular points. So just by applying the right voltage there, we've kind of created two things that behave like atoms, so two areas on this silicon microchip where electrons are confined and they take on particular quantum states. And then we can get them to interact, and critically we can switch on and off the interaction between them. So these guys have built here a 2-qubit logic gate in silicon. So that's what this device is. It's got 2 qubits and they're gated. So it's the rudimentary building blocks of a quantum computer. So again, if this could be scaled up, then you could, in theory, have a very powerful quantum computer. Other types of devices that could be used for quantum computers are donor impurities. So donors are things like phosphorus, which are added to silicon to dope them N-type. And so the microchips that you have in your computer will have been doped with phosphorus to make certain parts of them N-type. And this is very well understood. But a lot of people are looking at building qubits out of these phosphorus impurities. So usually phosphorus in silicon. But in order to do that, you have to build a very special device. So again, these guys at UNSW built this device. So again, this is a 2-qubit logic gate. So this is working a different way to the quantum dot device. So here, these guys have got a source and a drain, so it's something that can supply current. And critically, right here, you can't see it in this image, but here is a blow up of showing a very tiny area. So you can see the scale here from there to there is 13 nanometers, and quite incredibly you can see the atomic planes of the silicon here. It's actually resolved the atomic planes of the silicon. And what these guys managed to do, which is pretty incredible, was place individual phosphorus atoms where they wanted. So there's a very special type of lithography that's needed, but they managed to place individual phosphorus atoms where they were needed in this device. So in order to have a qubit, you can't have a big load of phosphorus atoms. You need a single phosphorus atom. And so this device is a rudimentary device made based on 2 phosphorus atoms here. So these two atoms here, and these can be gated, so their interactions switched off, and this behaves as a 2-qubit logic gate. So this is something that, if scaled up, could be used as a large-scale quantum computer. So another really important application is quantum communication. So if someone were to build a powerful enough quantum computer, then it could break the secure encryption that's used over the internet. So maybe you do your banking. The encryption is done using that problem we looked at earlier, where you've got a big number and you want to find its prime factors. So it works on the fact that it's easy to multiply two prime numbers together. The multiplication can be done quite easily, but the factoring is very difficult. So the encryption is done because if you take that number that's been multiplied by two prime numbers, then you can't. It's very difficult to undo that. But if someone did develop a technology that could break that encryption, then one way to get around that is with quantum communication. So in this case, if you've got two people who want to communicate, call them Alice and Bob, so they've got some message they want to send, then from information theory, if you've got some particular message, so it would be some string of ones and zeros, that is your message that needs to be sent between Alice and Bob. So that could be sent over the public channel. So something that you don't care if someone intercepts it. And the reason you can do that is if you create a key that is at least as long as your message, so an encryption key, if you have to encrypt that message, if it's as long or longer than the message you're sending, then this message that you send will be indistinguishable from random data. So no matter how powerful the computer you've got, the most powerful quantum computer imaginable, then the message you send would be indistinguishable from random data. So the key is that you need to get your encryption key sent securely between Alice and Bob. So you send your key over a quantum channel. So this is the thing that needs to be sent securely. And so if you send it over a quantum channel, so send this information in quantum states, then because when a quantum state is read, it is destroyed, then if somebody intercepts, so if we've got Eve trying to intercept your message, if they intercept this data that you're sending, because the act of reading or measuring these quantum states that are being sent down a quantum channel destroys them, then no matter what Eve does to try and recreate that message, Bob can look statistically at the information that is received and be able to tell whether it's been looked at. So currently, the best candidates we've got for sending quantum information is the fiber optic network that sends light in the near infrared at 1.5 micrometers, and it works at this wavelength because of the element erbium. So the element erbium is used for amplification. So that's because in the erbium atom there are energy levels that have a separation of pretty much exactly 1.5 microns, which is the wavelength of light that is needed to be sent down optical fiber, because that's where it's got its minimum loss. So what I've been looking at in the research I'm doing is erbium implanted silicon. So I've been putting erbium into silicon by firing it, accelerating it very quickly, implanting it into silicon, and I think this would be a good material platform to develop quantum computing and quantum communication devices with. And one of the applications that I envisage for this is being able to have some interface between superconducting quantum computers and the optical fiber telecommunications network. So if we've got some really powerful superconducting quantum computers, and these operate in the microwave region, and the quantum states can be coupled to superconducting resonators. So this is an example of a superconducting resonator that I used, and what this is an LC circuit. It's an inductor capacitor circuit. So you can see there's two parts to it. This part is the capacitor. So this is just a pattern that's been drawn by lithography on top of a crystal, and these lines are written in a superconductor. So we've evaporated a superconducting material onto here. So this pattern here, this thing that looks like fingers that are locked together, so it looks kind of something like that. So this is our capacitor. So if you want to pattern a capacitor on a flat surface, that's the pattern that you make, and that has some capacitance, right? So it's like these are the plates here that can build up charge. But if we have interlocking fingers like this, it's like having lots and lots of plates in a capacitor. And this part is the inductor. Right, this is the equivalent of having our loop of wire. If we flatten it out, here we can build up a magnetic field, and this circuit will oscillate. So like we looked at earlier, an LC circuit, so where you connect up a capacitor and inductor, it'll oscillate at a particular frequency. And these superconducting resonators oscillate at microwave frequencies. So this particular one oscillates at about 3 gigahertz, so about 3 billion times per second. And because this is a superconductor, those oscillations carry on for a very long time. We've got very little loss of energy because this is a superconductor. So we have only very high Q factors. So once we set this oscillating, it will keep oscillating for a long time. And the idea is that we can have some quantum state encoded in this resonator. And if we wanted to have this superconducting quantum computer communicate over the telecommunications network, then we'd need something that could convert from this 3 gigahertz frequency to the frequency, well, we don't write it in frequency because it's so high. It's 1.5 micrometers. The frequency is actually sort of on the order of hundreds of terahertz of the light that goes down optical fiber. So we need to convert from 3 gigahertz electromagnetic radiation up to hundreds of terahertz electromagnetic radiation, which is the near infrared that's sent down optical fiber. And the way I think we can do that is by coupling these resonators to erbium in silicon. So in a magnetic field, the erbium atom can absorb microwave frequencies, and then these absorbed microwave frequencies can then influence the transition. So we've got our two energy levels where transition of an electron dropping down here, it gives off light at 1.5 micrometers. In a magnetic field, these levels split up. So I've exaggerated that massively. But in a magnetic field, this splits up, and that splitting is can be sort of on the gigahertz region. So we can couple, in theory, this splitting to the microwave frequencies of these superconducting resonators. And this shows an experiment where I did that. So what we did, we took our erbium implanted silicon, stuck it on top of this superconducting resonator, and put it in a dilution refrigerator, a bit like the one we showed at the start, and cooled this down to about 50 millikelvin, so about 50 thousandths of a degree above absolute zero. And then we sweep the magnetic field. So we've got a magnetic field in there. We increase the magnetic field and rotate it, and then we measure the Q factor of this resonator, so how long it keeps oscillating for. And then what this graph shows is a measurement of the Q factor. So each here is a dot, and that's built up of dots, which are a measurement of the Q factor. So the brighter the dots on this graph, the bigger the loss in this superconducting resonator. So you can see here we get this pattern here of loss from the superconducting resonator, and we can show that loss must be energy being lost into this transition of what we call the Zeeman transition of the erbium in the silicon. So this is exactly what we'd expect as a function of magnetic field and orientation if this was actually coupling to silicon. So what we've shown here is we have coupled the superconducting resonator to the erbium. So in theory then, if this was coupled to a superconducting qubit, and then this erbium atom then coupled to some optical fiber that could send out light, then we can convert quantum information in the superconducting qubits into light that could go down an optical fiber. So that's currently what I'm looking at the moment, and so you can see this stuff we're learning about LC resonators is relevant to cutting edge research at the moment. Right, let's finish there then. I'll hang on for a few minutes if there's any questions, but other than that, I will see you next week.